Hello everyone, welcome to COMP251 Data Structure and Algorithms. In this video, I'm going to continue our discussion about recursion and talk about the Fibonacci sequence and the time complexity of the function that we wrote for that, and some more example at the end. So this is the Fibonacci sequence, and remember we have discussed this recursive function for Fibonacci, and I have actually just written the iterative version of the Fibonacci as well for you here, just for as a comparison. In terms of coding, of course, this one is going to be much easier to read. We basically just written that recursive relationship that we have here. We wrote the base cases and the recursive relation here. And the iterative version, which actually just started with two variables, basically three variables only you need. K1 and K2 is always actually referring to the two previous values, and K3 is going to refer the next value that you calculate, and you can actually just calculate using a loop. It started from the 3 until you find the nth Fibonacci number. We started from the 3, of course, because the first two number is going to be 1 that we have initialized beginning of, outside of the loop. So if I compare this to, implementation in terms of the time complexity, I think it's quite clear that what is going to be the time complexity of the iterative version. You can see that the body of the loop has constant amount of work, and the loop will iterate from 3 to n, so it's going to actually iterate n minus 3 times, and each iteration is going to do a constant amount of work, so it is quite clear that this is going to be a linear time complexity function. So how about the recursive version? How can we actually investigate the time complexity of the recursive version? Before I show you that, that mathematical approach to find out the time complexity, I think this here is going to be very simple. I'm going to just remind you about that, simulation of running Fibonacci, recursive version of Fibonacci, for example, for the value of 6. Remember, Fib6 was calling Fib5, and okay, so this function call would be actually happening. Then you know that before actually just coming back to calculate Fib4, which is actually coming here, you need to first calculate Fib5. Then, we have done actually this discussion in the previous video. Then Fib5 will be actually just calling again Fib n minus 1, which is going to be Fib4. Then Fib4 will be calling Fib n minus 1 again. You can see that none of them actually yet reached to the base case. And Fib4 will be calling Fib n minus 1, which is going to be Fib2. That's going to be the base case, so Fib2 will return 1. Then Fib3 will actually come back and call Fib n minus 2. That's going to be Fib1, so this is going to be actually returning 1. Then Fib3 will be calculated, returning 2 to Fib4. Then inside Fib4, it's just like you are still in this line, so you will call Fib2 again. Okay, so if I don't want to actually just continue this fully, but this is the tree that the full tree of the recursive calls, and you can actually see that calculation of Fib6 using this recursive function that we wrote actually means that you have to calculate Fib4 twice, you have to calculate Fib3 3 times, you have to calculate Fib2 quite a lot of times. Okay, so, and the fact is, we don't really need to calculate all of these numbers again and again and again. But this recursive function will actually force us to do that. So if I let me actually just follow that, mathematical approach to calculate the time complexity and find the time function for this one. So the thing is, we are interested to know what is the time function for fib n. So let's actually just show that as t of n. We are interested in this one. So you have some if statement here that will actually just check that. So basically constant amount of work there. You have some addition between these two function calls, so a constant amount of work because of this addition. But the thing is, how much cost is going to be taken by this function call? This is going to be a function of the same type as the original one, so I can use the notation t to show that, and the size of the problem is going to be n minus 1. So when you're calculating n, this is going to be taking t of n time. Calculating fib of n minus 1 is going to take t of n minus 1. And then you have another function call here. And you can see that because of having add here, it's not like the Fibonacci, it's not like the binary search that you either go to call the binary search on the first half or second half. You are calling the function call, this function call and this function call, both of them. Now you can see that, for example, fib6 will be needing fib5 and fib4 both. So I need to keep counting this one. So first of all, this is going to be some constant plus t of n minus 1 so far. And also you have to add the cost of this function call, which is again going to be shown using t, and this is going to be of t of n minus 2. So in total, I'm going to have a recursive relation like this. And what is going to be the base case? The base case is actually telling you that t of 2, when you reach to 2, you know that it's going to be constant amount of work. You just actually just return 1. Okay, so this is the full recursive relation for the time complexity of Fibonacci. Okay, which I have actually written it here. How can I solve this one? The thing is, the formula is a little bit, complicated, and if I wanted to show you the exact steps of the, the substitution and fill it completely, it's going to be too much math, and this is beyond the scope of the course. I don't want you to be involved in too much detail here. I'm going to simplify this to be able to actually solve the relation. I'm going to simplify it and write it in this term, that because t of n is going to be equal to c plus t of n minus 1 plus t of n minus 2, I can just, simplify it and say that I can say t of n is going to be smaller than, you can see that I changed the equation, the equal equation, to this, that a smaller equation, that t of n is going to be smaller than c plus t of n minus 1 plus t of n minus 1. So you know that I actually just changed that t of n minus 1, n minus 2 to n minus 1, so that I can just add up these two terms and write it in this way. That so t of n is going to be smaller than c plus t of 2t of n minus 1. Okay, so this is definitely not going to give me the exact time complexity theta for t of n. I can't actually just calculate that, but it still gives me some information. You see that this is going to be smaller, so it's just like it gives me an upper bound. So still I can calculate t of n in terms of big theta. So whatever is the time complexity of this formula, this is going to be that O of something, or at least I can actually just find an upper bound for t of n. And that's going to be enough to give you this, this idea that how, inefficient this function is. This recursive function that we wrote. So far, you got this idea that this tree is very big. This tree is actually shows you that how much computation you need to do. For each of these, as a vision to give you this idea. Each of these function call is going to take a constant amount of work, right? Because they actually just involve in, this if statement here, and some, each of these boxes on its own would just take checking the this condition, this addition, and returning the value. But the thing is, this box will call this box and this box as well. So I can just say that for each of these boxes, for each of these function calls, you are going to have constant amount of work. But the total time complexity for you will be C multiplied by the number of boxes, number of function calls. Number of function calls. So for example, for 6, how many function calls I have? For n, how many function calls I would have? Okay, so that will be basically the time complexity. And by solving this relation that I have here, you would actually get the idea that what's going to be the time complexity of this. I mean, you should have already noticed that kind of this is going to be, exponential. This is too much computation. You can just think that, for example, if you are calculating fib, for example, 7, you are going to have another fib 5, for example, on the other side. So it's just going to exponentially grow. And I'm going to mathematically just show you that, yes, that is a correct sense. So if I'm going to solve this equation here, let me just, again, I'm going to just double, make some space here, and okay, so let me just delete all of these. Okay, so the formula that I'm going to solve is going to be this 2t of n minus 1 plus c. Okay, so I'm going to continue and keep actually just replacing this t of n minus 1 with something actually just using the same recursive formula. That's going to be replaced with 2t of n minus 2 plus c. So the whole thing here will be replaced instead of this actually t of n. So if I put that one here, that's going to be 2 multiplied by 2t of n minus 2 plus c. Another c outside. Okay, so what I'm going to do here is just take this one and replace it with its equivalent, which is going to be again 2t of n minus 3 plus c. So that's the result is going to be 2 multiplied by 2 multiplied by 2t of n minus 2. Sorry, this is going to be n minus 3 plus c, 1 inside, another c here, another c outside. Okay, just before we continue, let me simplify this formula a little bit. You can see that if you keep multiplying these two insides, you are going to get 2 power 3 t of n minus 3 plus this 2 will be multiplied to this c, so this is going to be 2 power 2c plus 2 power 3c, this one, Yes, I have 3 2's. Just 2 of them will be multiple. I'm so sorry that I actually just messed up here. Okay, so these 2 are going to be multiplied to this c, so this is going to be 2 power 2c plus 2c plus 1c. Okay, I just actually keep them here because this is an important relation for me. I mean, this is an important pattern that I wanted to follow. So it's, I mean, if you don't feel comfortable, just pause the video, write it down for yourself, simplify it. I'm sure that you would get the same formula. So far what I got after 3 steps of replacement, actually after 2 steps of replacement, is this one. So this is the formula that I get after 2 steps. If I continue and replace this term again, so instead of that I should write another 2 of n minus 4 plus c. So if I actually just replace that, I would get something like this: 2 power 4 t of n minus 4 plus 2 power 3c plus 2 power 2c plus 2c plus c. Okay, these terms are important for me. I wanted to actually just keep them in this way so it's going to be clear what's going on. So you can see that after each step, I am adding 1 power of 2 here. I am decreasing this one by 1, and I am adding another actually term of c, of actually powers of 2 and c here. So after k steps, I would reach to this situation that this is going to be 2 power k t of n minus k, right? This is going to be k plus 2 power k minus 1 plus 2 power k minus 2. These are all multiplied to c. Don't forget those c's, okay? Although they are not going to actually just change anything for me at the end. Something like this, okay? Which you can see that this series can be written in this way. This is going to be, okay, before I actually just write it down in that way, let me simplify something else. So after k steps, you reach to a formula like this. So when you stop, you would stop when this formula reach to 0. N minus k will be equal to 0. So when n minus k will be equal to 0, when k is equal to n, right? Okay, so I'm going to just replace that. When k reaches to n, the final formula that you would get is going to be 2 power n t of 0, this is going to be n minus n, plus 2 power n minus 1 c plus 2 power n minus 2 c plus until 2 power 1 c plus c. Okay, so what was that t0? Remember, we actually just discussed that in this recursive relation that we had. Where did I write it? Yes, here is the recursive relation. That t of 2 is c, or okay, instead of t0 I had t2. I could actually just, I used to actually use the n equal to 0 as the base, but it doesn't really matter. Let me actually just update this one so that you would see there is no basically difference. So just assume that this is going to stop at this possibility, right? So in that case, k is going to, when k reaches to n minus 2, you would stop. So in that case, all of these are going to be changed to, for example, this one is going to be n minus 2. This one is going to be n minus 3, n minus 4, and so on. Doesn't really actually change too much. Okay, I just wanted to be precise for you if you had any doubt about that. Okay, so this one will be replaced with another c as well. So in total, at the end, you have all these terms, which are all powers of 2. Even this one, this c, can be written as 2 power 0 multiplied by c. This is a 1, I mean, the coefficient here is 1, right? You can just replace it as 2 power 0. So in total, I can just simplify this formula as c multiplied by this summation of all the values from 0 to n minus 2 to power I. Okay, all these summations. I wanted to actually remind you about this summation. I'm sure that you have seen it in discrete math. That in total, if you have a summation, like let me actually just use a different color and put it here. If you have a summation like I equal to 0 to, for example, k, 2 power k, this is going to be equal to 2 power k plus 1 minus 1. Okay, so remember this summation. This is actually very important. This is from discrete math. If you don't remember it, just write it down somewhere, and you will get used to it. I mean, in computer science, you will see this series of numbers, this summation, in many places in the future. So this is important. Just like the other summations that I have used in the, like for example, this summation, this is also going to be very important from this summation, which is going to be n to n plus 1 divided by 2, or for example, the other one, I equal to 1 to n I power 2, which is going to be n to n plus 1 to 2n plus 1 divided by 6. These are very important formulas for us that you need to actually just always remember them. There's no other way to deal with that. Just remember them. Okay, so one thing. So far, I actually just got that this summation is going to be 2 power n minus 1 minus 1. Okay, and you will multiply that to c. So at the end, what you get here is that as t of n is going to be 2 power n minus 1 c. Okay, plus, or minus c, doesn't really matter. So what you are thinking about this in terms of O, I mean that time complexity, I mean, t of n is going to be smaller than, I shouldn't say actually equal, but t of n is going to be smaller than this. So in total, I can say that t of n is going to be in O of 2 power n. Yeah, or guess about being exponential was correct. This, the Fibonacci, I have actually just write down the full proof here for you. The Fibonacci, the recursive actually version of the Fibonacci can actually just go, exponential. Although this is not exactly 2 power n, I mean, if I wanted to be exact, this is going to be 1.6 something power n, but still this is going to be, the exact time complexity for this recursive relation. But as I told you, this is going to be too much math to show it here. And at the end, we don't really care because although this is not 2, but this is some number greater than 1, right? And because this is greater than 1, this is going to be exponential. This is not exactly 2, but it is quite big. I mean, after a couple of actually steps, you will see that the size is going to grow very fast. So yes, this recursive version of Fibonacci is not going to have the same time complexity as the iterative version. Although in the previous cases, like for example, the binary search, the sequential search, the time complexity of the recursive version and the non-recursive version were the same, but in this case, the time complexity of recursive version is not equal to the time complexity of iterative version. Iterative version is quite fast. This is going to be linear. The recursive version is going to be exponential. So, but you might actually just think that why there is that much difference between the recursive version and iterative version. The reason is actually behind this picture, that you can see that in the recursive version of this, computer will calculate some of these functions repeatedly, and although it doesn't really need it. For example, this fib4 here, it has been calculated here. Why am I actually calculating it again? I'm calculating it because you have written the recursive code in this way. So the computer doesn't know that you have actually calculated that. So we can modify this recursive version basically by, caching all of those calculation and storing them somewhere. So if I, for example, all of these fib4 that I have actually calculated, or fib3 that I have calculated, if for all of these values, for example, if I calculated the nth number, I store it in some array, and then later on use it. So if I use this caching idea, I can make my recursive, I can fix the issue with this recursive version and make it quite fast. So what I'm doing is that I will create an array outside of the recursive function. This is going to be initialized as all of them will be actually 0. So when it is 0, it means that it hasn't been calculated. Before starting, the main body of the function, what I'm doing is that I'm just adding, a sanity check at the beginning of the function. I will just double check that if the value of the cache hasn't been calculated, if it has been calculated, which means that you are getting something greater than 0 from the array. If it is 0, it means that it hasn't been calculated, right? But if there is anything greater than 0, it means that it has been calculated. And so you just take it from that cache. Okay, so you are not going through the rest of the code and calling these function calls again and again and again. So now you can see that I have to store these values at some point, right? So whenever I reach to this point that, okay, just assume that the number hasn't been calculated. If it hasn't been calculated, the main body will be calculated, the previous actual body. You check the value of n. If it is greater than 2, you come here, calculate fib n-1, calculate fib n-2. So this function calls will be happening, and then you store the number in the appropriate index. Okay, store it before you return it. So later on, if you need it, here this sanity check will avoid you from calculating it again. So using this new version of Fibonacci, with this actual idea of the caching, what would happen to the function calls? So the function call of 6 would actually, the function call 3 will be actually looking like this. Fib6 will come here, the value of n is 6, you check the cache hasn't been calculated, right? So it's going to be 0. It comes here, checks the value of n comparing to 2, it is greater than 2, so it comes to this line. It will call fib of 5, so fib 5 will be called. Again, fib 5, it actually first check the cache. It hasn't been calculated before, so it will actually come here. The value of n is greater than 2. It comes here. Fib n-1 will be called, so fib 4 will be called. Again, In FIB4, you check the cache. It hasn't been calculated. So you compare the n is greater than 2. You come here, you call the FIB3. So FIB3 will be actually called. FIB3, again, you check the cache. Cache hasn't been calculated. N is greater than 2. FIB2 will be called. So FIB2 will be called. FIB2 is the base case. So it can be actually just checked out here. So it returns 1. FIB3 will call this one as well. It returns 1. Okay, it actually returned to 3 will be calculated, and be careful, 3 will be stored as well. So in the cache, it will be actually just something like this, that it's going to be 0, 1, 2. Inside 3, so 2 will be stored. The rest of them is still 0. 4, 5, 6. Okay, so what would happen? Here 2 will be returned to FIB4. FIB4 will call FIB2 as well. FIB2 will return 2. You can see that in this implementation, we are not storing FIB2 and FIB1, but it doesn't really matter because anyway, they are going to be cached in the base case and they don't have any recursive call. So that's totally fine. So FIB4 will be calculated as the summation of this one and this function call. This is going to be 3. Okay, this is going to be 2, 1, 3. The result will be stored in the cache. So FIB4 will be calculated as 3. Okay, let me just clean up here a little bit. Okay, 3 will be returned to FIB5. In FIB5, you were here, you are done with this function call. Another function call will be called. Okay, look at this. FIB3 will be called. FIB3 will be called, and here FIB3 is not going to call the recursive functions because it has the cache. The cache will be actually returning the value of 2, and so here we just avoid calling that 2 function calls here. So that cache is avoiding those, the rest of actually growing the 3 here. Then 5 will be calculated as, okay, 3 will be returned, 2 will be returned. The value of FIB5 is going to be calculated as 5. It will be written here, and it will be returned to FIB6. Again, in FIB6, you are done with this function call. You are going to call FIB4. In FIB4, the value from cache is going to be taken. 3 will be returned, and the value in this cache is going to be replaced as, for example, 8 as well. So if you are calling a larger tree, you can see that this is going to be, your tree, instead of being a complete tree, it's just like it's growing one way. It's just like I have cut all of these branches, all of these right branches have been actually cut. Okay, so they are not going to grow. Even if you had actually a bigger tree like the FIB7, this one, and then this one will be actually cut because FIB5 has been calculated. So this one is not going to grow. So what is going to be the time complexity in this way? This is very important for us. If I come back and say that, okay, so what is the time complexity of, not this one. What is the time complexity of this version, this new version of the recursive Fibonacci? I probably cannot actually just go with that simple recursive relation that I found, that T of n is equal to C plus T of n minus 1 plus T of n minus 2, clearly because some part of the calculation will be stopped here. So if you wanted to calculate the time complexity of the function after doing this, this caching, you should actually just do it in this visionary way, in this way that you actually just think about how much computation you are doing. You should think about this tree shape that you have and say that, okay, how many times Fibonacci of each of these numbers will be calculated. For example, if I'm actually calculating, for example, if I'm calculating fib n, how many times I will calculate fib, for example, 3, how many times I will calculate fib 4, how many times I'm calculating fib 5, all of these numbers. So you can see that the actual calculation for fib 3 will be only once, right? Because whenever you calculate it, you put it in the cache. So you never calculate it again. The same for 4. All of this calculation will be done only once. And so if you are calculating fib n, how many Fibonacci numbers you will calculate? You're going to calculate all the Fibonacci numbers from 1 to n, exactly one time. And how much is the cost of calculating each of them? The cost of that is going to be just the addition of the cost of the previous two numbers, right? Because I am avoiding the recursive calls. I'm reading actually them from the table. So in total, I can say that the number of function calls is going to be linear to the number or to n that I'm actually calculating. So the number of function calls is going to be, for example, c multiplied by n, or the number of function calls is going to be, in fact, based on this tree, I can see that this is going to be exactly 2n, the number of function calls, and in each function call you are going to have fixed amount of work. So this is going to be multiplied to some fixed amount of work. This is going to be theta of n. So by fixing this caching idea, I could actually make my recursive version of Fibonacci theta of n. I could make it linear function. This idea of the caching is very important because this is basically the basic idea of the dynamic programming, a very famous problem-solving technique that you will learn about it in COMP251. That's the design and analysis of algorithm. We will see that many interesting problems can be solved using this idea. We first find a recursive relation, and then we will actually just find out some repetition of computation, and using this idea of the caching, we would avoid redoing that calculation. So I'm not going to continue, talk more about this because this is beyond the scope of this course. It will be discussed in higher level course. Okay, so just to finish this lecture, let me just review a couple of previous examples that we have seen, just see what is the time complexity of these functions. So the factorial function. What is the time complexity? Just assume that this is going to be written as t of n. I am going to find a recursive relation for this, for the time function of this function. You can see that I have some comparison here, and then after that, so this is going to be a constant, just a comparison, and then you have some multiplication here, some decreasing here, right? And a function call. This is going to be the same function as factorial, so I can show it as t of, what is the size? The size just been decreased by 1, so this is going to be t of n minus 1. So the total time function is going to be c plus t of n minus 1. And the base case is clear, that t of 0 is going to be c. So we have already solved similar recursive relation like this, right? Remember the sequential search that has exactly similar time function, right? So if I solve this one, again, I would get t of n. So this is going to be the time function, and this is going to be the time complexity of that. And it is clear, although you don't have that explicit loop, but because of this function call, you just repeatedly decreasing the size of n, and you would actually keep that multiplication through the function calls. So of course calculating n factorial would need a loop, would need to actually just multiplying all the numbers from 1 to n, and that's going to be a linear function. This was one of the other examples that we have seen last week, printing all the numbers from 1 to n in descending order, basically from n to 1. So what's the time complexity here? Again, this is going to be t of n. I'm going to actually find the time function for this recursive function. Here I have some comparison. I have a printing statement. This is going to be again a constant amount of work, and I'm calling the same function here. So I'm calling the same function. This is going to be shown as t. What is the size? The size has been reduced by 1. So again, the time function is going to be some constant plus t of n minus 1. And what is the base? The base here is going to be when n reaches to 0, so t of 0 is going to be constant. Again, the same time function. If I solve it, I would reach to t of n. So another example, this is a recursive function to calculate exponentiation, for example, to calculate x power m. So I have two arguments. X is the base. I'm going to calculate x power m, and m is that power that I'm calculating. So the recursive relation for this formula, that I can actually write it in this way, that x power m is going to be x multiplied by x power m minus 1. So you can see that this is the same problem as x power m, but the smaller size, right? M became smaller. So that variable that shows the size of the problem is not x, but it is m. Okay, so the name of the variables are not really important. If it is m or n, we basically show the time complexity based on n, but it doesn't really matter if you show it as m or n. So the size of the problem here will be shown using m, but I just wanted to follow the same rule that I always use n. So basically m is going to be n for me. This is the size of the problem. So to calculate the time function here, you can see that I have written actually two base cases, but basically, just even the first one was going to be enough. So what is going to be the time function? T of n. What is going to be t of n? You have a comparison here, you have a comparison here, you have a multiplication here, and you're just a decrease here. So a constant amount of work plus, you can see that I am calling the same function and I am reducing the size by 1. So t of n will be equal to c plus t of n minus 1. Again, you can say this is exactly the same recursive relation. What was the base? The base, you can say that, okay, t of 0 is going to be just constant, and this is going to be the base. What is the total time complexity? This is going to be linear. We know that we have already solved this recursive relation. Another recursive function. Okay, we have seen this example before. This recursive function, if you actually just try it for these examples, you will see that this recursive function basically solve the, checks if the input string is palindrome or not. What is palindrome? Palindrome means a string that reads the same from left and right. So for example, kayak is going to be a palindrome. this string is going to be palindrome, because if you write it from left to right, or if you write it from right to left, they are going to be the same. Okay, but this one is not palindrome and this one is not palindrome. And you actually, if you check it, you will see that this function properly checks the palindrome. And the nice thing about the, again, the implementation of this function is that you can see, and let me actually just explain the recursive relation, because this is important here for me. For palindrome, the recursive relation that I have written is something like this, that you would say a string S is palindrome if the first and the last character are the same. Okay, so if you have a string, you can just say that, okay, a string S is palindrome if the first and the last character, so a start, and so let's, instead of actually a start, let's actually use the same variable names that I have here. If the first, let's just call this one I and this one F. Your string is palindrome if S index I is equal to S index F. Okay. And not only that, this part of the string is also palindrome. So basically, I mean, I can actually show it in, what is the easiest way to show it in terms of this, just the pseudocode. This is going to be like, for example, this part should be also palindrome. So checking that this part is palindrome is the recursive part, right? That's, you are just calling the same function. But how I am calling this recursive function? Exactly like the, the binary search that I showed you, the implementation of the binary search or the sequential search, the recursive version of them. A string is going to be like, in fact, a string is going to be an array of characters. So when I'm working on strings, just like the way that I was working on array, I try to avoid creating a new string in a recursive calls. So instead of just creating a new string and say that, okay, create a new string for this part and passing that to the function, I am just showing it using these two variables that shows the starting point and ending point. So what would happen if I am going to indicate this part of the strings? So I would indicate that by actually increasing the size of I. You can see that in this function call. This is going to be I plus 1. This is going to be F minus 1. So this is showing just inside the string except the first and the last character. Okay, so you see that I'm actually just changing the size of the string that I'm working on by increasing I and decreasing F. I'm emphasizing on this part because the time complexity of this palindrome function is going to depend on the number of characters that you have in the string. So at the beginning, when you are calling the function, you are calling it with the value of I equal to 0 and the value of F equal to the length of the string minus 1. So you can actually just think about it as n minus 1, right? If you have n character in your string, that's going to be n minus 1. So when you are calling the function originally, this is going to take how much time this is going to take? This is going to take t of n. I am interested to find what is the recursive relation for this t of n. Let me use a black color. So now I'm actually just looking at the body of the function. The body of the function, it is going to have a comparison here, a comparison here, Okay, so again, you can see that the body of the function is going to have just constant amount of work and a function call here. So I'm looking for t of n, but this one is going to be a function of the same type, but different size. What is the size? We can see that originally when I was 0 and f was n minus 1, the size of the problem was actually n, right? So when I'm changing I and f, I'm changing the size of the problem. By increasing I and decreasing f, increasing I by 1, decreasing f by 1, it's just like I am removing one character here and I'm removing one character here. So how many characters in total I'm removing? 2 from n. So actually the size of the problem will be n minus 2. So this function is going to be the same function, but taking the same amount of time. This is going to be the same function, but the size of the problem is going to be decreased by 2. So I'm going to get a time function like this. T of n is going to be t of n minus 2 plus c. You see that you might actually just think that, okay, this is a new time function because I'm not getting, the previous ones usually was t of n minus 1, but this is slightly different, right? Just let me follow and see that what is going to be the base case. You can see that in this implementation, the base case is happening here, that if the value of I became equal to f, or the value of I became greater than f, in that case, this equation became false, right? This, condition, and you would reach to this line and return true. So this is going to be the base case. When the value of I is equal to f or it is greater than f. So when it will actually happen, what does this mean? What does this mean that the value of I is greater than f or it is equal to f? You can see that if I go back to this, if I go back to this, let me fix this part and let me clean this. If I go back to this picture, you can see that the I is going forward, f is going backward. It is kind of similar to the way that a start and end in binary search was moving, right? A start was moving forward, end was moving backward. But the difference here is that in the binary search, a start was not moving just by one, end was not moving by one. They would just jump. For example, they would jump to the middle of the array. But here, I and f just change by one. Each time I will actually just move from here to here, and then from here to here, and f is just moving backward by one. So they are just moving towards each other. In each actually step, they are moving in this way. So either at some point they would reach to each other, so I will be equal to f, or I will pass f. In fact, if you try the function over these examples, you will see that the value of I will reach to f if the length of the string is odd. If it is odd, at some point I will reach to f, which basically it tells you that, okay, you reach to the middle token. And it doesn't matter what is the middle token. If you are looking for a palindrome, if you just have one character is going to be palindrome, right? You just actually immediately come here and return true. If the length of the string is even, if n is even, for example, like in this case, you would see that the value of I at some point became greater than f. So if n is even, at some point I became greater. So it's just like will actually move to 1. It's just like, for example, if I show it to you here, that's going to be easier. That at the beginning, I is here, f is here, then I is here, f is here. Then at some point, I will actually just reach to here, f reaches to here, which means that I became greater than f, okay? It is because the length of the string is even. If the length of the string is even, it means that at some point, the value of I became greater than f, which means inside, the size of the string that you are checking is 0. That's going to say that, okay, no, the size is 0. If the size of if you don't have any character in your string, again, this is going to be the base case that is true, right? So a string of length 0 is a palindrome. So basically you just return true in that case as well. So it is clear that the base case for our function is going to be n equal to 0 or n equal to 1. So it doesn't really matter. So you can actually just write it in this way. T of n equal to c is going to be constant amount of work. So at the end, what is important for me is that this is going to be the time function. This is the time function. And what is going to be the time complexity? If I do actually keep replacing here, let me actually just write it down for you. Okay, let's add an empty. Okay, this is the formula. T of n equal to T of n minus 2 plus C. What I'm doing is that I'm going to replace this with T of n minus 4 plus C. Okay, don't be confused. Let's just replace that. T of n will be T of n minus 4 plus C plus C. Keep replacing this part. This is going to be T of, be careful. The formula tells you, this is something that I have seen in many cases, the students just get confused. This is n, and you are just putting the n here. So this T of n minus 4 will be equal to T of n minus 6 plus C. Okay, n minus 6, nothing else. The reason is that you just subtract it from 2. So n minus 4 minus 2 is going to be n minus 6. So the result that I am getting here after 2 steps is going to be T of n minus 6 plus C plus C plus C. Okay, just let's actually do it one more time. This is going to be, this part will be replaced with T of n minus, okay, T of n minus 6 will be equal to T of n minus 8 plus C. So T of n is going to be T of n minus 8 plus C plus C plus C plus C plus C. Actually, let's just simplify this. You can see that so far I got 4 C's. And this is basically T of n minus 2 multiplied by 4. Okay, I just wanted to tell you that that pattern that is happening is here. 2 multiplied by 4. Let me actually just do it one more time. So T of n, let's just replace this one. This is going to be, this is T of n minus 8, right? If you replace it, it will be T of n minus 10 plus C. Okay, so T of n will be equal to T of n minus 2 multiplied by 5 plus 5C. Okay, we can see this pattern here. So after 5 times I reach to this, after k times I would reach to this formula. T of n is equal to T of n minus 2k plus kc. So when you are going to stop, when n minus 2k reaches to 0, which means that k is equal to n divided by 2. Okay, so T of n will be equal to, so in this case, this part will be another c. This is going to be k plus 1c. What is k? K is n divided by 2. So what I would get at the end is T of n will be n divided by 2c plus c, which completely clear here is that this is going to be some constant, right? You can actually just say it as this is n multiplied by c divided by 2. This is a constant, so in total T of n is going to be theta of n. This is going to be linear, right? It is not like binary search. It's not going to give you the log of n. The reason is that when you are changing the size, you are just increasing I by 1 and f by 1. So you are just decreasing the size by 2. Okay, so it's just like you have a loop that goes from 0 to n and just increase the size of I by 2 each time. Although the number of iterations is going to be n divided by 2, but at the end it's going to depend on n linearly. So it's going to be theta of n. So that's it for the recursion and our discussion about the time complexity of recursion.